Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome. I'm pleased to introduce Diego Coman, who's a professor of economics at Dartmouth College and a faculty research fellow at the NBER. That's the National Bureau of Economic Research, and they're the people who call recessions. So when you hear we're in a recession, usually about 9 months after that started, they announce it. That's their job. Professor Coman has published extensively on a topic I find fascinating, and that's the effects of the adoption of technology on economic growth. And he's arguably the world's foremost expert on this topic. And this is a topic, as a technology company, it's a topic that's of very great importance to Microsoft. In fact, reflecting that, he spent more than an hour with Satya yesterday. It would be helpful if I could read my own notes, wouldn't it? Dr. Coman's research has been supported by the Gates Foundation, the National Science Foundation, and many others, including Zentrum for Europäische Wirtschaftsforschung, something let's just call it ZEW. Dr. Coman has advised the Prime Minister of Malaysia and consulted with the European Central Bank, the World Bank, the IMF, the Federal Reserve of New York, Citibank, the Danish Science Ministry, and the Economic and Social Research Institute, and finally the government of Japan. He received his PhD in economics from Harvard University in the year 2000, and prior to teaching at Dartmouth, he's taught at NYU and the Harvard Business School. At the Harvard Business School, he won awards for innovative education programs in Peru and Malaysia. Let me tell you about 3 logistical issues. There's a live Yammer feed. If you're on the Skype, you should be able to see the Yammer feed directly. There's a link on there's also a link on the invite. So if you're carrying a laptop or phone and want to put something on Yammer, you're welcome to. But there will be time for questions at that mic. There's also a help link if you're having trouble, again, at the bottom of the invite, and we just sent out an update to the invite. And then we have this microphone here for questions at the end. So without further ado, let me introduce Dr. Diego Coman.
Thank you, Preston. Thank you for this great introduction, and thanks a lot for your hospitality, for inviting me these days, and for taking such a good care of me. It's going to be hard to go back home and realize that nobody takes care of you in academia. So I've spent lots of time studying technology, and especially the consequences of the use or adoption of certain technologies. And I've studied that in various contexts, in the context of business cycles. Why is it the case that when certain recessions hit the economy, productivity growth slows down? And now we are, after 6 or 7 years, way worse than what we were before the beginning of the Great Recession in terms of productivity. And I've also studied that in the context of long-run growth and why there are rich and poor countries in the world. And so in the vein of this second line of research, I'm going to be talking about this paper that I've been working on for a while with my friend Martin Mestieri, who is an assistant professor at Northwestern. And the motivation for this paper is quite straightforward. If you look today in the world, you look at the richest countries and the poorest countries, huge difference in their income per capita. You look at the top 5%, bottom 5%, the ratio of their income per capita is approximately 50. We need to understand why is it the case that some are so rich and some are so poor before we can change that, before we can make the poor countries reach a level of development that we feel comfortable with, or that they feel, happy with. So to understand why this difference in income exists, it's kind of helpful to think about how they have emerged. Okay? And so one fact is that if rather than measuring difference in income today, you went back to 1800s, or a couple of centuries ago, the difference in income between the rich and the poor countries will be much smaller. Okay? So again, you do the same comparison, top 5% of the countries, bottom 5% of the countries, difference in income approximately by a factor of 5 rather than 50. Okay, so income per capita gap between rich and poor countries has increased by a factor of 10 over the last 200 years. And so that increase in the gap is called the Great Divergence for obvious reasons. And so any explanation for the Great Divergence should really account for not only the current difference in income that we see, but the much smaller difference in income that we saw 200 years ago. So we should really try to target the process of creation of that income gap. We should try to understand that process. And that is the focus of this paper. I'm just going to look at one particular hypothesis and see how far I can go with it. Okay? The hypothesis I want to explore is whether the Great Divergence has been a consequence of changes in the way technology is diffused across countries. Okay? So this may seem very vague, but I will flesh out the hypothesis for you. Okay? So I want to measure, to test this hypothesis, I want to measure technology. I want to look in the eye to technology and see how technology was 200 years ago and how it is today, and how countries adopted technology 200 years ago and how they adopt it today. Okay? Once I have measured technology, I can really explore whether there's been any trend, any pattern in the process of technology adoption which differs between rich and poor countries. Okay? I can try to explore whether technology adoption has changed over time differently in those countries that have ended up being rich and in those countries that are poor. Okay? And then once I have done this exercise, I can try to explore what are the consequences that these possible changes in technology diffusion have had for income differences across countries. Okay? I can move from first looking at technology, measuring technology, then exploring how technology has changed, and third, exploring the consequences of these changes in technology diffusion. Okay? So there's the 3 steps that I want to pursue today with you. Okay? And then at the end, if we had time, we can speculate about why technology has changed. Okay? But that's not a priority for me. Now, before we start, there is a potential problem, like a red flag that comes out quickly when you think about this hypothesis, which is that we have the notion that now technology arrives everywhere, okay, in rich and poor countries. And 200 years ago, probably that was not the case. Technology were invented in rich countries. It took a while for them to reach poor countries. And so that notion, would push you back in terms of this potential explanation, okay, because it would suggest that before technologies didn't reach to poor countries, now they do reach to poor countries. So technology should be a force that creates convergence on income rather than divergence on income. Okay, so that's something that I want you to keep in the back of your mind and keep it in mind when I look at the data. Okay, good. So how can we measure technology? Well. When I was in grad school 20 years ago, we used technology as a justification for everything, for business cycles, for growth, and yet we never had a direct measure of technology. And so let me guide you through the different alternatives that we have had to measure technology. The first one is the one that we had 20 years ago, which is technology is measured as a residual. Okay, what does it mean? Residual means that we don't see technology directly, but we see the outputs, for example, labor productivity. Okay, we see how much output we produce per capita in a given country. And we see some measure of the inputs, like, we see how much capital there is, we see how many workers we have, okay? And so, one possible proxy for technology is this residual, okay, which is basically what remains in labor productivity after we take into account the inputs that we use in production, okay? And so you take inputs, you apply them your technology, and then you end up with some outputs. So technology would be like, what allows you to take the inputs and transform the output. So at a conceptual level, that seems like a plausible way to measure technology. You take labor productivity, divide by your inputs, what remains is your technology. Now, that's a very imperfect measure, of course, because we really don't see technology, we see a residual, okay? And that residual may be contaminated in so many different ways. Maybe your measures of the inputs is not perfect. Maybe you use more or less intensively your inputs without measuring that. Maybe there are factors other than technology that affect how you transform your inputs into your outputs. For example, climate, institutions, history. I mean, there may be tons of things that may affect that relationship. And so this is a very poor place to settle in our quest for a measure of technology, okay? A much nicer measure was developed in the early 50s. There was this, fantastic paper by Zwiger-Likes in 58, where he developed a measure of technology that consisted in looking at a particular production process or technology and measuring how many people, how many companies were using that production process relative to the sample of companies that could potentially use it, okay? So it's what I call the number of potential adopters relative to the number of potential adopters. And so that's a measure of how extensively the technology has been used in the country or in the region. That's a direct measure of technology because we are looking at whether you have or not the technology. So in principle, it seems like it passed the smell test. One problem is that it's difficult to construct. It's difficult to construct because it requires to have micro-level data. You need to have information on each company in the country or in the sample to know whether they have the technology or not. That's a potential problem. Second, it's not clear what's the number of potential adopters. I mean, that's, is what? It's like the total number of firms in the economy, only some firms in the sector. Like, it's very difficult to measure that, to, come up with a good measure. And finally, one problem with this measure is that it doesn't capture how intensely we were using the technology. So you may have the technology, you may have a technology here in Microsoft, okay? But it's something that only Preston teams uses, or it's used throughout the company. That's an important margin. And indeed, we have some historical evidence by Clark arguing that this margin is critical to understand difference in productivity across countries. He has some evidence on textile technologies early in the 20th century. So difficult to construct. As a result, after 50 years of research, we have a handful of measures for a handful of technologies for a handful of countries. So not sufficiently dense to understand any long-run trend, any pattern that we see across countries, okay? And not perfect, okay? So after that, I decided together with some co-authors to build our own measures of technology, okay? Now, our own measure of technology, it's a direct measure of technology, so I'm trying to measure either the inputs associated with a technology or the outputs produced by a technology, a specific technology. And I built on aggregate data, on country-level data. And in that way, I avoid the difficulty of using micro-level data, which is a huge impediment towards measuring technology for many technologies and for many countries. So the result of this effort is the chat dataset. Chat dataset, it's a dataset that I put together with a co-author, Bar Hobain, who is now at the University of Arizona, where we measure the diffusion of more than 100 technologies for over 150 countries over the last 200 years. Okay? starting for technologies invented in the 18th century and going all the way until technologies that we use these days, like the internet, cell phones, or computers. Now, here are a few examples. Number of computers, tons kilometers transported by train, number of telegrams, number of spinning spindles, number of internet users, you name it, okay? So the nice thing is that these are important technologies, have been invented continuously over time, many different sectors, and that if we understand how they have diffused, how they have been used in the economy, potentially we can learn something about growth dynamics, okay? So let me show you a plot, okay? This is the logarithm of kilowatts hour produced each year in a number of countries, okay? So this is my measure of electricity. The US, Japan, Netherlands, and Kenya. And this is how our diffusion curves look like. This is the representative sample. So you are going to have these concave curves that at the beginning, as you would expect from a concave curve, they are very steep, and then over time they flatten and they converge towards a certain trend. Now, we spend many, many years looking at these curves, many, many years. And then after paying close attention to them, we realized that one property that was approximately correct, to a first order with these curves, was that when you take a particular technology and you compare the diffusion of the technology in different countries, to a first order approximation, these curves are just the same curve, translated, move around horizontally and vertically, okay? And so if that's the case, that's an important property, because if that's the case, I can take this complex nonlinear curve, this object, and reduce it to just 2 parameters when it comes to understanding how it differs across countries, okay? And so that's something that is going to come handy in a second, okay? So in the meantime, you can wonder, why technology matters. What dimensions of technology may matter for productivity growth? And so there are 2 dimensions of technology that matter for productivity growth, at least in a very vague sense. So first, you need to have the technology. If somebody has invented something, but it hasn't arrived to my country, nobody is using it in my country, then that's not going to impact at all our productivity. That's not going to make us more productive. So that's the first dimension. It's called the extensive margin, okay? And so it's related to how many years it takes for a technology to arrive to a country. Second dimension has to do with, once it has arrived, how intensively are we using it? Like, is it something that plateaus at a low level? That means that, very few people end up using the technology? Or is it something that plateaus at a very high level? That means that many companies end up using this technology in the country. And so if more people end up using the technology, that means that it's going to have a greater impact on productivity, and it's going to be more significant for the country. While very few people end up using the technology, then it's going to be almost irrelevant. It arrived, but nobody uses it. So this is what I call the penetration rate or the intensive margin, okay? Now, you would like to find ways to measure that in my technology measures. And intuitively, they are related to these horizontal and vertical shifters, okay? So let me show you. Let me show you again the curve, okay? So these curves, again, they have this curvature that is very large at the beginning, and then it flattens. This is a steep slope at the beginning, and then it flattens. There are many reasons that could create this particular shape, but that's not important. The important thing is that this shape is relatively parsimonious across countries. What that means is that I could measure how many years it takes for a technology to arrive to a country by comparing the slopes of the curve at different points in time in different countries, okay? So I could, for example, come here and say, okay, so this is the computers per GDP in the US and Vietnam. At this point in the US, we had this particular slope, okay? How many years it took to Vietnam to reach a similar slope, okay? Those years this gap in time, what tells me is the difference in the adoption lag between the US and Vietnam. Okay? It tells me how long it takes for the technology to arrive at a similar curvature in two different countries. So that's how I can measure the adoption lag, the years it takes for the technology between the invention and the use of the technology. That's the first dimension. Second dimension has to do with the intensity of use. Okay? The intensity of use, again, it's going to depend on many factors, but eventually I want to measure these vertical shifters that explain differences in the eventual use of the technology across countries. Okay? And so for that, what I can do is I can come here and I can look at the gap between the curves once they have stabilized at a particular distance. Okay? And that's going to tell me something about the differences in the penetration rate of the technology. Okay? So in other words, diffusion curves have a shape that is very parsimonious across countries. The key differences are these two parameters, the horizontal and vertical shifters, and I can use these horizontal and vertical shifters to infer how long it takes for a technology to arrive to a country and how much people are going to use it or profit from it once it has fully diffused. Okay? That's basically the intuitive argument for how we're going to measure the adoption lags and the intensity of use. So this is another example for steam and motor tonnage ship in the UK and Indonesia. Okay? Similar exercise. So what's the plan of the talk? Well, my plan is the following. First, I want to show you how technology looks like, how the intensity of use and the adoption margins look like when I look at my data. Then I want to study how these margins of adoption have changed over time across countries. Is there any pattern, any long-run trend that we should be aware of when it comes to technology diffusion? Third, I would like to compute the consequences of those trends in the diffusion process. I would like to understand what are the implications that this evolution of the diffusion process has had for productivity growth across countries. Okay? And then again, if we have time, we can talk more about what may be the underlying forces that have driven those trends. Okay? Okay. So far I've been explaining you these things as if this was a class of drawing. I draw this curve, I have this horizontal shifter, this vertical shifter. You don't need to do any math. And I think to explain the intuition, you don't need any math, but I've done the math. Okay? So we have developed all the specifications that we use to estimate this model as the outcome of a relatively simple economic model of diffusion. Okay, it's a very intuitive model. It's probably the simplest model you can write. It's a model where technologies are invented in the world. Each technology has a variety of vintages, as you know. And each vintage is better than the next one. Each technology is better than the next one. And so there are these adoption lags that determine how long it takes for a new technology or for a new vintage to arrive to a country. And then there is the intensity of use that determines, once the technology has diffused, how intensively we are going to use it in the country. Okay? So that's basically the structure of the model. Okay? Once you put that structure, what comes out is an expression for how the cloud should diffuse. Sorry, I didn't mean the cloud. I meant spindles. Okay, but that would fit the cloud very well, by the way. So basically, here I have the log of the number of computers in the country, and that's going to depend on a number of features that are important. Okay, first. We're going to have more computers in richer places than in poorer places. That's something that has to do with your demand. Okay, you are richer, you want to have 3 cars. If you are poor, you want to have half a car. Okay, then there's going to be some time trends. Okay, there's going to be some time trends that probably capture the fact that technology gets better and better over time, and therefore it becomes cheaper, and so on and so forth. Then there's going to be a term that is nonlinear that captures the adoption lag. Okay, so this is exactly the intuition I described you before. When the technology has just been invented and I start adopting it, this term is very steep as it's been longer since the technology was invented. This is the invention date, this is the adoption lag, so this is the time of introduction of the technology in the country, and this is the current time. Okay, so this gap is how long ago we started using the technology in the country. When this is very small, we're taking the log of 0, this is very, very steep. As time goes by and we have been using the technology for a while, this is much less steep. Okay? Then finally, there is a term here that captures the possibility that places where wages are higher, the cost of using the technology is higher. Okay? So again, simple specification that comes from first principles, but that captures very nicely all the intuitions I just given you with the plots. Okay? And so the intensity of use, the adoption margin is going to be measured from here, from these changes in the curvature. The intensity of use is going to be related to this intercept, which means that once technology has fully diffused and we have converged to these log linear trends, how intensely we're using the technology. Okay? So that's basically what this is. Okay? Okay. So now I want to take this model and bring it to a data, estimate these two margins. So for each technology country pair, I'm going to estimate how long it takes for a technology to arrive to a country, and once it arrives, how intensely we end up using it. Okay? Now, I'm going to do that with using my data set for 25 major technologies invented over the last 225 years. Okay? And so they run from ring spindles in 1775 until the internet that was invented in 83. That's what Al Gore said. So this is how it looks like. So these are for each of the 25 technologies. Okay, this is the invention date. This is how many countries I have for the particular technology. This is the average adoption lag. Okay, so this is like I have one adoption lag for each country and for each technology. So this is the average across the countries for that particular technology. Okay, how many years it takes on average for a technology to arrive somewhere after it has been invented. And this is the dispersion of the adoption lags across countries for that particular technology. And this tells me something about the distribution, the percentile 10, the percentile 9, the interquartile range. Okay? So first thing to note is that adoption lags are long. Okay? So the average across all these estimates for all these technologies is 45 years. Okay? So historically, it has taken a long time for technologies to arrive to places. Now, they haven't been constant. They have changed over time. Okay? There are strong patterns. So if you look at the average adoption lags for the early technologies, they were very, very long. Okay? 100 years for spindles, for steam and motor ships, railways, and so on and so forth. But then for the newest technologies, they have been much faster. On average, 10 years or less. Okay? So there's potentially some interesting patterns there that we would like to explore. Okay? Okay. What about the intensive margin? So the way I measure the intensive margin, I was too fast here, but basically the way I measure it is I measure the intensive margin. So I'm going to be looking at different types of countries and different classifications. Okay? The baseline analysis, I'm going to be using classification that was constructed by a famous historian, Agnus Madison, where he looked at what he called Western countries, which are some countries in Western Europe, the US, Canada, New Zealand, Australia, and Japan. Okay? He calls these Western countries, versus non-Western countries, which are the rest. Okay? And so to measure the intensive margin, because this is impacted by the units at which I'm measuring technology, I have to measure it relative to a baseline for each of these technologies. So what I do is I just measure the intensive margin always relative to the Western countries. The Western countries is my baseline. And so when you see a 0 in the intensive margin, that means that the technology is being eventually used at the same rate as the average of this group that Madison called Western countries. Okay? If it's a negative, it means that it's eventually used less than that. Okay? And if it's a positive, it will be used more than that. These are in logs, so negative means that we're using it at less intensity. Okay, so intensity of use for the 25 technologies. Well, you can see that on average, obviously, because we have Western and non-Western countries, and in Western countries, technologies are used more intensively than in non-Western countries. The average is negative, okay? So it's minus 0.6. It means that it's used approximately 60% less than in the average Western country. It's helpful, to see how big is this dispersion. It's helpful to see the interquartile range, okay? So if you look at the 10th percentile versus the 19th percentile, so this is approximately, that's pretty large. That's here. For the total, this is a 1.9 gap in logs across all the technologies. The e to the power of 1.9, I mean, you probably can do it in your head, okay? I have to use the computer. 17, okay? So the gap in the use of technologies between country that is on the 90th percentile, a country that is on the 10th percentile, a factor of 17. Now, that's huge. Remember, we're talking about income, and income being up to a factor of 50 between the top 5% and bottom 5%, okay? So we are really in the realm of big numbers, okay, when it comes to productivity differences. Okay, again, we would like to understand whether there's been any action here over time or not, okay? And so that's what I'm going to turn next. Now that I've shown you the estimates at this high level, I want to work with them a little bit. Okay, so what do? Let's start with the adoption lags. Okay, I'm going to show you a plot that does the following. For each of the 25 technologies, I'm going to be plotting the technology in the invention year. Okay, and for that technology, I'm going to be plotting three numbers, the median adoption lag, the median adoption lag for the Western countries, and the median adoption lag for the non-Western countries, okay? So for example, this is spindles. The median adoption lag is here. It's approximately 100 years. For the Western countries, it was a bit more than 40. For the non-Western countries, it was more than 160 years, okay? Huge adoption lag for these all technologies. I do that for all the technologies. And just visually, you can see how these adoption lags change over time quite dramatically. They really decline everywhere, okay? They used to be around here, and then, they have declined, and they are now around here, okay? Much smaller. But you can see how they decline much more in poor countries, in non-Western countries, than in Western countries, to the point that by this time, you really need to squint a little bit to see the difference between the two. Well, here the differences are quite obvious. Okay? I can formalize this intuition. I can document that better by running what we call a convergence regression. Okay? So this is very simple. I'm going to regress the log of the adoption lag on the year of invention of the technology. Okay? And I'm going to normalize by 1820. Okay? So this is going to be the number of years since the number of years since the invention of the technology relative to 1820. And I'm going to run this regression for the full sample, for the sample of Western countries, and for the sample of non-Western countries. Okay. So for the full sample, you have it here. What you see is that clearly there was some reduction in the adoption lags. So technologies invented at a later invention year, they are going to have a much smaller adoption lag, okay? Again, this is in logs, 1%, so if you multiply by, say, 150 years later, that's a big, big difference, okay? This constant, this informs you about the adoption lag that we would predict for 1820, okay? So if this constant is smaller, that means that we would expect to have a smaller adoption lag in 1820. Now, what happens when we look at these subgroups of countries, Western versus non-Western? For Western countries, well, we also saw some decline in the adoption lags, as you could see in the plot. but is smaller than for the average. Okay? Adoption lags have declined, but at smaller rate. For non-Western countries, you can see that there is a huge reduction in the adoption lags. The rate at which they are reduced is much larger than for the Western countries. Okay? They also started at a higher level. Okay? You can see how the constant was higher for the non-Western countries than for the Western countries. Okay? That means that in 1820, the average adoption lag was much larger in non-Western countries, in poor countries than in rich countries. Okay? But since then, they have converged dramatically. Okay? And they are still a bit larger than for Western countries, but the gap has narrowed very, very significantly. Okay? So that's the first set of results. The first set of, that's where we are reaping the profits from our effort. Now, what has happened to the intensive margin, to the intensity of use? Well, this is the plot. So again, for each technology is plotted in the invention year, and I have 2 bars, the intensity of use for the Western countries and for the non-Western countries. Okay? Now, recall that the way I have normalized the adoption margin, I was normalizing it to the level of the Western countries. So not surprisingly, the level of the intensity of use for Western countries is around 0. Okay? That's just my normalization. So really, what is important here is to look at the intensity of use of non-Western countries. Okay? And so what you can see here is that initially, the gap in the intensity of use between Western and non-Western countries was relatively small. It was positive, so there was more intensive adoption in Western than in non-Western countries, but they were not huge. Okay? For example, in 1820, the gap was approximately 40%. Okay? Not a big number. But then, as time has gone by, there's been divergence in the intensity of use of technologies. What that means is that once technologies arrive to a country, now they end up being used much more in rich countries than in poor countries, while before, eventually, they would be used in rich countries a bit more than in poor countries, but not to the extent that they are used today. Okay? Now, to formalize this, you can look at this line. Again, it looks at the evolution of the gap in the intensity of use between rich and poor countries, and so here more intensity of use is good. So a negative means that Western countries or non-Western countries are falling behind Western countries as we are looking at newer and newer technologies. Okay, so that's a force that potentially could lead to divergence in income. Okay, so just to summarize the findings of the empirical analysis so far, adoption lags are larger in poor than in rich countries, but the gap between the two has narrowed over the last 200 years. The intensity of use is larger in rich than in poor countries, and the gap between rich and poor countries has increased over the last 200 years. Okay? So what I would like to do now is to take these facts and use my simple model to explore what are the implications of these trends for the evolution of income, productivity, across countries over the last 200 years. Okay? I would like to understand whether these help us explain the great divergence or not, whether these are peanuts in the big scheme of the great divergence. Okay? And so again, to do that, I'm going to take the model, I'm going to simulate it, plugging in this number that I've estimated. Okay? So it's a very parsimonious exercise. Now, before I do that, before I look at the great divergence, it's kind of interesting to look at the beginning of all. So to look at 1820. Okay? This is the beginning of the period where income gaps between rich and poor countries started to diverge. And one question I can ask is, okay, so when I look at the technology in 1820, do I explain the gap in income between rich and poor countries or not? Okay, so my model is very specific about what should be the gap in income given the technology. Okay, it says, well, when you look at Western versus non-Western countries, the relative income should be given by this expression. It should be a function of the adoption lags in non-Western relative to Western countries. So if there is a larger adoption lag in non-Western countries, that means that the technology they will be using will be older, and therefore they will be less productive than the technology used in Western countries. And it should be also a function of the relative intensity of use of non-Western countries for the technology. So If non-Western countries use technologies very intensively relative to Western countries, the gap in productivity between Western and non-Western countries should be smaller, okay? And should be impacted in this way. So I have numbers on this, and this. I calibrate these three parameters to the standard numbers that we use in macroeconomics, so nothing fancy. And this is what happens. So the intensity of use, again, in 1820, the gap is approximately 40%. The gap in the adoption lags is 49 years. So the gap in 1820 between rich and poor countries is 49 years. So when you look at the data, Madison's data, the income gap between Western and non-Western countries on average was 1.9, okay? So that means that Western countries were on average 90% richer than non-Western countries. When you plug these numbers that I've estimated using micro-level data on my specific technologies into this expression, that is the expression that my model generates for income productivity differences, I nail it. I get exactly 1.9 years, okay? That was clearly not expected, clearly not intended. So that seems like a promising way to start, okay? My model explains initial differences in income, but that's not the goal. I mean, nobody wanted to explain that. I want to explain how the gap increased, okay? So this is like, like a teaser. So what do? Well, I need to generate an industrial revolution, okay? So how does the industrial revolution work in this model? Well, basically, remember, I mentioned that in this model we have new technologies being developed every moment in time, and each technology will have newer versions of the technology that also develop every moment in time. So what industrial revolution is in this model is something very simple. It is a moment in time where the rate of development of new technologies accelerates, okay? And so that moment in time, it's 1765, when we invented the steam engine, when Watts invented the steam engine. And we have an acceleration from the growth rate that we have in the data before the Industrial Revolution to the growth rate that we see these days of 2%, okay? So basically the growth rate for the technology frontier, for the frontier of technology that we have in the world, it increased by a factor of 10. Okay, that's basically what we see. Then I take, remember, this is a model of adoption. Okay, so this is what goes on the frontier, but what matters for you is not what goes on in the frontier, but how quickly you are going to bring these technologies and how intensively you are going to end up using them. And so I plug in the trends that we have estimated, and I simulate the economy. And this is what comes out. So the top panel, I'm plotting the growth rate of output or labor productivity, which is the same thing here, for the Western countries and the non-Western countries in the model. Okay, so this is what the model generates after you plug in the diffusion patterns that we have estimated using micro-level data, technology-level data, sorry. And so this is what you see. You see that, here we had the Industrial Revolution, okay? But it takes a while for new technologies to be brought into production because we have these long adoption lags. So nothing happens in the Western countries, in the blue countries, or in the non-Western countries, in the green countries, okay? Nothing happens for a long time. Now, adoption lags are shorter in Western and non-Western countries. That means that we will start bringing the new technologies faster in Western than in non-Western countries. So we should expect an acceleration of productivity growth in the Western countries before than in the non-Western countries, okay? And that's what we see here. The blue line takes off because we have started to bring into production the Industrial Revolution technologies, okay? That happens around 1830 or so, okay? And then productivity growth starts to increase in the Western countries, and that, because nothing has gone on yet in non-Western countries, we had an increase in the gap in productivity growth between the Western and non-Western countries. And that's what the bottom panel measures. The bottom panel measures the gap between these two lines, okay? Now, around 1860 or 70, non-Western countries start to grow a little bit faster, okay? But not that much faster, okay? Why is that? Well, that's the case because, sure, we are bringing in new technologies, but we are using them a bit less intensively than in rich countries. Okay? In rich countries, we bring them and we use them more intensively than in poor countries. So remember, the intensity of use is greater in rich countries than in poor countries. Okay? The peak gap takes place around the turn of the century, okay? A bit after 1900. We had a growth rate in Western countries that is over a 1% greater than in non-Western countries. Okay? After that, the gap starts to reduce a little bit because of the dramatic reduction in the adoption lags. Adoption lags have been declining. They decline big time in poor countries. Okay? However, we always have, throughout the exercise, we have greater growth in Western countries than in non-Western countries. Okay? So this is what the model predicts. How does this compare to the data? Well, let me show you first some numbers. Okay? So the first column here is the average growth rate in the model for Western countries over this period of time, over this period of 180 years. So this is Western countries, non-Western, and this is the gap between the two. Okay? The second column is what we see in the data, what we see in Madison's data. So you can see that the two are pretty close. Okay? So sure, Western countries grow a little bit less in the model than what we saw in the data. Non-Western countries, they grow approximately the same. Okay? The gap in productivity growth, the average gap in productivity growth between Western and non-Western countries is 0.65 in the model, 0.75 in the data. Okay? That means that productivity growth, as induced by the changes in the diffusion process, explains approximately 80% of the gap in productivity growth that we see between rich and poor countries, between Western and non-Western countries. Now, it's interesting to cumulate that. So to see in terms of the great divergence how much we're explaining. And so if you cumulate those differences, what that means is that the income gap between Western and non-Western countries is going to increase by a factor of 3.2 between 1820 and 2000. In the data, it increased by a factor of 3.9. Okay? So again, we're explaining 80% of the great divergence just through the dynamics of technology diffusion over the post-war period. You can slice the data more. So for example, you can look at by period. Okay? So far I showed you what happens over 180 years. You can slice it between the period that went until before World War I and after World War I, Western and non-Western, in the model and in the data. Okay? So what you see is that the model tends to generate a bit less productivity growth than what we saw in the data in this first phase. Okay? That's not surprising. You know, probably there were other things that went on, like for example, lots of capital accumulation, human capital accumulation, so on and so forth. So I'm very happy if not everything is due to technology. Okay? Still, the gap in productivity growth between Western and non-Western countries in the model, even in this first period, is almost 0.5 percentage point per year. The data is less than 0.6 percentage point per year, so they are pretty close. And then in the second period, in the period that runs over the 20th century, the gap is much closer. It's much closer to the data, so it's much larger and much closer to the data. In the data, it was 0.93% per year. What the productivity, the technology diffusion dynamics generate is approximately 0.84 per year. Okay? Another way to look at this is by slicing the countries. Okay? So far I look at rich versus poor countries or Western versus non-Western countries. What if I look at the whole distribution? Okay? So rather than looking at just these two groups, let me show you what happens if I divide the distribution of countries by income quintiles. Okay? So there's like the bottom quintile, there are 5 quintiles. So in green, what you see here is the level of productivity in each of these quintiles relative to the poor countries. Okay? So you can see that the gap, this is for 1820, the initial gap was a bit less than factor of 3 between top quintile and the bottom quintile. In blue, you have the implied quintiles in productivity based on the simulations where I feed in the diffusion processes that I've estimated in the diffusion data. And what you see is that this explains in 1820 a gap of a bit more than 2, like 2.2, between the top quintile and the bottom quintile. Now I'm going to fast forward. I'm going to show you 3 periods of time where I'm feeding in the model and computing the productivity. This is 1913. Again, green, the data, blue, the model as driven by these diffusion patterns. And you can see that the 2 lines are very close. So, we don't get to explain everything that we have seen for the top quintile, but we get very close throughout the simulation. And this is what happens in 2000. In 2000, the 2 lines are almost one on top of the other. Here there is a bit of a gap. So the factor of productivity of the top quintile versus the bottom quintile is approximately 27%, and a factor of 27, and in the model generates a factor of 26. Okay, so dramatic accounting, dramatic generation, or dramatic consequences in terms of productivity and productivity growth over 200 years from the consequences of these trends in technology diffusion. Okay, you can do the same thing by continents. I'm not going to bore you. The numbers are similar. You can take into account the initial productivity differences, your factor, how much you explain, again, number of 80%. You can look at the super poor countries, the bottom 10% of the countries. What about African countries? What about poor countries in South Asia? Well, the model or the initial differences in technology are very close to explaining, actually over-explain a little bit, the initial difference in income. Income or productivity as driven by technology diffusion increases by a margin or the gap between the bottom. So this is the gap, the increase in the gap between the Western countries and the countries in the bottom 10%. Okay, so the Western countries' income increased by a factor of almost 6 times larger than the countries in the bottom 10%. In the data is 6.3. Okay, so as a result, at the end, what we see in the data, which is that the income gap between rich countries or Western countries and countries in the bottom 10% of the income distribution, which is a bit less than a factor of 18. Difference in technology diffusion explain approximately a factor of 17. Okay, which is very, very close. Okay, so the last 3 slides, I would like to use them to explain you what's going on, what's the mechanism. Okay. And so to do that, remember, we had 2 adoption margins, the adoption lags and the intensity of use. Okay? So the exercise I do now is I'm going to take these 2 margins one at a time. Okay? So first I'm going to feed into our simple model the changes in the adoption lags. Okay? Remember, adoption lags were converging over time. They were very large at the beginning, especially for poor countries, and then they become much more closer for both rich and poor countries. What happens if the only thing that happened in the world was that we changed the adoption lags? This is what you should see. You should see that income differences start to increase a little bit for rich countries relative to poor countries, so this is productivity growth. But then, as adoption lags narrow dramatically in poor countries, the growth rate of poor countries should take over the growth rate of rich countries. And starting a bit before 1900, we should see a convergence in productivity growth, okay, actually in productivity between rich and poor countries. So this plot nicely shows this. This is, again, the gap in productivity growth between rich and poor countries. The gap increases early on, as adoption lags are shorter in rich than in poor countries. But then quickly, the gap is, the sign of the gap is reversed, and we start seeing faster growth in poor countries than in rich countries. Okay? Obviously, the only thing that has changed between this plot and the one I showed you before is that now I'm keeping constant the intensity of use. Okay? I'm not allowing for any changes relative to the initial level of the intensity of use. So the difference between this evolution and the other one, it's purely driven by the divergence of the intensive margin. Okay? You can do the opposite exercise, which is, let me shut down the dynamics in the adoption lags. Let me keep constant the initial adoption lags. and I feed in only the intensive margin. What would happen? This is what would happen. What you would see is that rich countries grow at approximately the same rate as before, but poor countries, they basically grow much less than before. And the gap between the two, it's greatly increased relative to the baseline. Okay? Why is that? Well, that's because, again, I'm not allowing poor countries to benefit from the fact that now technologies arrive to poor countries much faster. Okay? The only thing that happens here is that they still receive the technologies very, very late in the process, and when they receive them, every time newer technologies are going to be used less intensively than what they are used in rich countries. Okay? So, let me conclude. Basically, the main finding from this analysis is that the great divergence, it's a consequence of a change in the diffusion process. Okay? And this change has the following features. The rate at which technologies arrive to countries, the adoption lags, those have converged over the last 200 years. Okay? Now technologies arrive everywhere very quickly. And that was not the case 200 years ago. So that has led to poor countries to grow faster than what they used to. Okay? However, when technologies arrive to countries, rich countries, they use the technologies in many more different ways and by many more people, many more companies. So as a result, they take greater advantage of those technologies and productivity growth can be much greater than in poor countries. That gap in the usage of technologies was not so evident 200 years ago, but today is very evident. Okay? When you feed those two dynamics that we have estimated using technology-specific data, okay? You know, this is like each technology, each country, one at a time, okay? When you feed them into a standard macro model, they generate basically 80% of the gap between rich and poor countries that has increased over the last 200 years. So basically, it generates 80% of what we call the great divergence. Okay? So that's basically where I would like to leave it at this point. Thank you.
So we have about a half hour for questions. Why don't we reward those who came into the room by starting with the room, and then we'll switch to Yammer and switch back. And you're welcome to come up to the mic.
Thanks so much for the...
That doesn't seem to be on.
Yeah, thanks so much for the insightful discussion. At the very beginning, you mentioned that there is lots of combined effects, and you're trying to account only for technology. But now thinking about the intensity of use, it seems like this is the one that's more prone to this lumping effect. Like, for example, like the level of education, the social, culture, political situation in these countries will affect how the intensity of use. And this also will affect the GDP. And how can we account for that in our analysis? So this is one question. The other one is that I believe, like, with all this experience in advising like different countries, how different countries can kind of come up with better kind of rate of use of the technology. Okay. Thank you.
So those are great questions. Fantastic, thank you. There are three questions, which is fine. So question number one. What drives the intensity of use? Okay, many things could drive the intensity of use. So, in principle, okay, intensity of use basically what measures is how much we use a particular technology. So it could, a priori, it could be driven by taxes, expropriation. So if you are going to be expropriated when you build a railway, okay, then you are not going to do it. Or if you are going to expropriated when you ship your merchandise to a railway, then you're going to, install, particular technology that is going to take advantage of the railway that you have there. Okay, so for sure that could have an impact. Some people have argued that geography matters a lot. Okay? If you are in the tropics, there's going to be disease, and therefore people are going to be less productive than if you are in another climatic zone. That should affect the intensive margin too. Okay, now these explanations, I think, and so again, I'm not taking a stand of what drives the intensive margin. Okay, so in principle that's fine with me. But when I think about what could be driving it, one thing that I think is kind of interesting is that what I see is that the intensity of use has diverged. Okay, so in other words, if I look at one of these factors that is affecting one technology versus another, a new technology today versus a technology invented two centuries ago, I should try to, potential explanations should try to account for the divergence of the intensity of use. Okay, and many of these explanations that you presented, especially institutions, geography, they don't seem to have diverged. Okay, clearly geography is the same. Okay, so geography hasn't changed much over the last 200 years. Maybe from now on it will change, but until now it hasn't changed. Institutions, we tend to believe, all the political scientists, when they have tried to measure the quality of institutions, all the data they have, which is not perfect, but is what we have so far, suggests that there's been convergence in the quality of institutions. There is more and more democratic countries. There is fewer and fewer dictators. Institutions in the West haven't changed much. In African countries, Latin America, there are more checks and balances, and so on and so forth. And so it doesn't seem that line of explanation for the drivers of the intensive margin are going to be that successful. Okay, so we can probably talk about what I think is the key driver of the intensive margin. Actually, it's related to the work I've been doing in other countries. But then, before I get there, let me talk about your second question. The second question is, how do I then take the technology data and bring it to, or use it to answer the question of what drives productivity growth? Okay, and so your question is a question that all the economists in the room will understand well. Okay, but it's a bit subtle for non-economists. Okay, your question is, if you use econometrics to run a regression where you put the intensive margin on the right hand side and productivity growth on the left hand side, then there are many potential omitted variables that may drive the intensive margin and productivity growth, and therefore you may conclude that productivity growth is driving the intensive margin is driving productivity growth, but that may be just a spurious correlation between the two. Okay, and that is 100% right. Okay, and this is why we don't run regressions to conduct that experiment. Okay, I just take my model, plug in the data I've estimated from the diffusion of individual technologies. Okay, so I haven't used aggregate data. I've controlled for all sorts of aggregate stuff like GDP, all sorts of things that my model tells me I should be controlling for. And I plug them and I simulate it. Okay, so it could be the case that this intensity of use, it's peanuts as compared to the great divergence. It could be the case that the intensity of use or the adoption lags, have converged rather than diverged. So because I estimate this technology by technology, country by country. So there is no need to have any trend. I'm not pushing the data to have any nice pattern. It could be like all noise, because I'm taking one by one, and so it could be that. But happens to be the case that they have this particular shape, this particular pattern, and that the pattern is very significant. And once I plug that into a model that tells me when technology is this, productivity is that, which is a standard growth model. I don't need to estimate anything. Basically, a model with 3 parameters. I get these dramatic effects on productivity growth. Okay, and we can leave the third one for later. Otherwise, I'm going to use all the time.
You have a camera?
Hi, thanks. I'm just wondering, in addition to the adoption gap and the penetration rate.
I think go to I know they have to.
It's really close. Oh, okay. Yeah. Okay. So in addition to the adoption gap and the penetration rate, is there any effect in the mode of usage of the technology? Like, for example, if we take the internet, for example, in many of the poor countries, the penetration rate may have accelerated very rapidly due to mobile devices and so on, but it may not be used in a productive way. Like mostly social media or whatever. So how does the model account for that, or is it really impactful or significant?
Yes, I think that's an important observation that probably is very important for certain technologies, like for example the internet. That seems like when I see my children, it seems like an obvious technology where this matters. Unfortunately, that's something that is not taken into account. So if that was something that you added on top of the measure that we have for internet users, which is the number of people that use the internet in the country, which is a very poor measure, but is what we have been able to measure, then probably the gap in the intensity of use of internet between rich and poor countries probably would be larger. Okay, but that's a speculation. So I haven't been able to do it. So in general, some of these measures of technology could be refined a little bit. At least conceptually, I can think of better measures. The challenge is to have a measure that is widely available for many countries for a long period of time, and then also for many technologies. So spend countless hours thinking about what was out there and digging. But yeah.
Hey, Diego. Hey, Sid. I've got two questions. One's really a suggestion. I think so the first one I think is possibly incredibly valuable to Microsoft. One of the policy issues that we face around the world is trying to measure and argue to policymakers the social value to new technology, obviously the cloud, the internet. And as you know, there's a bunch of economic studies using econometric methods that try to measure, say, what's the incremental value of having an increase in 1% internet adoption. I always tell people here, don't raise your right hand because of the econometric issues that you mentioned before. But I can see a way to skirt that with your model, which is that your model does so well actually estimating or simulating the actual growth profile. Suppose we were to drop a technology from the model. We take your 25 technologies, we drop the internet, and we look at the difference in the projected growth profiles with and without the marginal technologies. Would that be a way to estimate here's the value of the single technology, or is that not kosher given the simulation technique?
Well, I think I see what you mean. Fortunately, we take a stand on the potential growth effects of technologies. So basically, that's something that actually is very standard in macroeconomics. Okay, so we believe it's something called balanced growth path or the steady state, and we have strong priors about what the steady state is. Like the U.S. has been growing at 2% per year. That seems like the steady state for the U.S. or for a rich country. Okay, and based on that, you can back out what's the growth rate of technology. Okay, what's the growth rate of productivity gains associated with technology. And so here, the type of exercises that I think would be more interesting is suppose that you don't question, these trajectories for the aggregate economy, okay? But you take one technology, okay, and you slow down the diffusion of that technology or technologies in that vintage, okay? So in our case, you have a continuum of technology, so one technology per se is not going to do anything. Then I could tell you what's going to be the impact that's going to have on the growth trajectory of the country. And so that's the type of exercises that you can conduct here, Or alternatively, I could take two countries that have different adoption patterns, and I could tell you how they have fared based on the simulations of the model, which account extremely well for the evolution of the whole distribution of income across countries. So and I think that would be what would give some power to the exercise. The fact that this seems like powerful way to think about long-run development dynamics. So.
And the second question is, this is really striking, the slowdown in the change in adoption rates, right?
It's relative. So it's,
It's
relative to the
relative to
the rich countries. So it could be that the rich countries have been using technology much more than before.
Right.
So I cannot tell which one is which.
So here's a hypothesis that's probably easy to shoot down. If I think of like the Bessemer oxygen furnace or the shuttle, not really much of a network externality.
Yes.
But as technology evolves over time, it seems the later technological innovations have more of a network externality, and that just could lead to slower adoption because of the lower GDP, and that might be explaining the change over time.
So I appreciate that hypothesis. I mean, I think maybe it's perfectly plausible. Fortunately, I have sufficient technologies to understand the patterns. I don't think I have sufficient technologies to understand why the patterns take place. 25, it seems like a small sample size for any economic analysis, but it's sufficient to infer patterns, and everything we have here is extremely significant. I think network effects are important, especially and complementarities between technologies. I mean, many of these technologies built on previous ones, so mechanically, if you don't have electricity, it's hard to use computers productively. If you don't have computers productively, it's hard to use the internet, and so on and so forth. So those mechanics, for sure, are playing some role. Coming back to the first question, I think another factor which is important here is technological knowledge. Okay, so if you think about what it takes to productively use a technology, requires having lots of knowledge about that technology, about complementary technologies, about business practices, about business models that can take advantage of the technology, and so on and so forth. And that's a factor which I think may have diverged over the last 200 years, because I don't think that we knew much about that in developed economies 200 years ago, and today we know a lot, or much more than before. And so one feature of that factor is that you accumulate it by using the technologies. So it's prone to lead to path dependence. Those that had some advantage initially in using the technology because they were using like the technologies invented in the first industrial revolution, develop greater knowledge to use, say, industrial technologies, and that made them more prone to develop new uses for the new technologies developed in the second industrial revolution, and so forth. And also, it led to the creation of, when you had the first technologies coming in, people wanted to formally educate workers, so it led to the creation of engineering schools. I think MIT was built around the time of the second industrial revolution. So, there is all sorts of mechanisms that perpetuate those patterns when it comes to thinking about knowledge, okay? Knowledge, education, and formal and informal education, and so on and so forth. So those mechanisms, I think, are potentially important. On a related note, I've done some research looking for the impact of, or studying the impact of interventions in the amount of knowledge, technological knowledge that countries have. So, for example, after World War II, the U.S., for strategic reasons, wanted to foster the development of countries like Japan, Korea, Singapore, and Germany. Okay, and so had all sorts of interesting programs like the Marshall Plan, plans to bring managers and engineers from Japan to look at U.S. plans, plans to let Japanese license U.S. technologies, multinationals going to Korea, to Singapore, to Taiwan, and so on and so forth. And so those were programs that intervened directly into the amount of technological knowledge that these countries had. And so what I've seen is that those interventions led to disruptions in the diffusion process. And so, for example, it led to a dramatic reduction in the adoption lags in these countries in new technologies, not in all technologies, but in new technologies there was a big reduction in the adoption lags, as you would expect. And so those are evidence that speak a little bit about this mechanism. But that's not something which I've tried to pursue, like, it's in its full length. So, yes.
Something else which has changed and might make a difference and create a permanent gap in this kind of adoption is the increasing importance of tradables. So especially in knowledge goods and services, there's a local scope for deploying technology. In 1820, technology in England was not a good substitute for technology in Brazil.
Yeah.
Now, much more so. So there's only so much you want to do because you may as well import.
Absolutely. Absolutely. Agreed.
So we have a question from Yammer, and it's, in your work, the left-hand side is usually work productivity per capita or productivity. And have you thought about, have you done work where the left-hand side might be average lifespan or mortality, infant mortality or literacy or something like that, where some technologies might directly improve those measures that don't show up in productivity numbers?
So that's a great question. The very first paper I wrote in economics was called Convergence in Health. That was before anybody had done any work on that. And I published it in a very obscure Spanish newspaper, Spanish journal. That was when I was an undergrad. Since then, I haven't looked at health until recently. So I'm working with some people at Dartmouth now studying the diffusion of some health technology, implantable defibrillators. And we are looking at the effect that they have on mortality rates. But that's a very interesting story because it seems that some people over diffused that technology, and they had wrong incentives in certain parts of the country to use that technology too much, and as a result, mortality rates are positively associated with the diffusion process, not negatively associated. And then over time, in those places you see that the diffusion actually went down again. So yes, health is interesting, but it's bound to deliver surprises.
All right, well, thank you very much.
Thank you very much.